everybody, welcome back. We're going to finish up 6.1, exponential growth and decay. We're going to learn how to write an equation to model exponential growth and decay and predict outcomes. All right, so first of all, just taking a look at what this all is. Here's a situation here. The population of a large city is about 4.6 million in the year 2010. It grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over that 4-year period? Well, first of all, at year 0 or 2010, we start at 4.6. So this is like my starting point right here, right? And so this is like my start, okay? Right here, we're starting in year 2010. Then in the next year, we take that initial value, 4.6, and we're going to add this factor right here. We're going to take 1.3% times 4.6. And remember, 1.3%. To get a decimal, we're just going to move it to the left twice. Okay, so or you divide by 100, either way you want to look at it. So that's going to give us this 4.6 plus 4.6 times 0.13, and I can take this 4.6 and factor it out. 4.6, that's going to leave me with 1 plus 0.13. Okay, so if I factor that out, I'll leave me with 1 here and then the 0.13. That's how I get this 4.6 times 0.13. Okay, so notice that this is an exponent of 1 right here. So now in the next year, I'm going to take this value right here and multiply it by my rate again, 1.013 again, right? Because it's growing by 1.3%. So I take my final value at the end of the year previous and multiply it by the percentage again. That's going to give me 4.6 times 1.013 to the second power. And then I'm going to do the same thing again, right? I'm going to keep on multiplying by that percentage. So the next year it's going to be this value, 4.6 times 1.013 squared, multiplied by 1.013 again, making it a cube. The fourth year it's going to be 4. So you can kind of see as time goes by, that's the number of years that's gone by. Okay, so this is what we have down here and how you write an equation. And my population, our ending point basically, equals our beginning point. This is where we start, times our growth factor. Okay, so it's our growth factor. We're going to talk about the difference between a growth factor and growth rate in a minute. And this is my time, years since 2010. Okay, so if the population continues to grow at the same rate, what will the population be in 2040? Well, we started in 2010, so we're basically just going to subtract 2010 from that. We're going to get 30 years gone by, right? So that's how we end up with time equals 30 down here. So we're going to plug in that 30 into our equation. Okay, our population is going to be 4.6, our starting population, times our growth factor to the 30th power, which is 30 years. Okay, so I'll get my little calculator here and we'll plug that in there. So 4.6 times 1.013 to the 30th power. 30th power, and that gives us about 6.8 million in population. Okay, so approximately 6.8 million people in 2040. Okay, all right, so a factory purchased a 3D printer in 2010. The value of the printer is modeled by this function right here, so it's decaying, okay, where x is the number of years since 2010. What is the value of the printer after 10 years? Okay, so we have f of x, so we're going to go f of 10 equals 30 times 0.93 to the 10th power. Now notice it's 30 is our starting point, right? That's where we started at. So I don't know if it was 30,000 or $30. I can't imagine 3D printer costing $30, but So 30 times 0.93 to the 10th power. So that's going to be $14.52. So it's going to be approximately equal to $14.52 is what it's worth after 10 years, or thousands. I'm not sure if it's in thousands or not. Okay, so now we're going to just kind of take a look at these growths, exponential growth and decay graphs and what they all mean. Okay, so first of all, it's in this form right here. Remember, it's kind of a times b to the x, right? If b is greater than 1, it represents a growth function. if b is between 0 and 1, and notice it's not equal to 1, because remember in the other lesson the other day, if it's equal to 1, it's no longer an exponential graph anymore, it's a line, okay? But if b is greater than 1, but we have this negative x here, it actually does turn into a decay, because if I have y equals, let's say, 3 to the negative x, remember this negative exponent makes this flip around, so that actually becomes 1/3 to the x power. So even though it looks like it's going to be growth, it's going to be decay, because it's a 1/3 anyway, okay? And then the b term is called either the growth or decay factor, one of the two. And these graphs, it goes from left to right up as a growth graph, and from left to right down is the decay graph, okay? Here is some more information on these graphs, okay? This always is my final amount. My initial amount is A, my starting point. Now this is the difference between rate, a growth rate, and growth factor. It's very important, okay? My growth rate is always in decimal form. So say a 25% growth rate, we're always going to make sure we write it as 0.25. And so I take 1 plus 0.25, and that would give me a growth factor of 1.25, right? Growth factor. So the 1 plus the rate gives me our growth factor of 1.25. Okay, so the difference between a growth factor, which is being multiplied, and the rate, which is like usually the percentage. Okay, and then decay is a little bit different, because notice that this one is 1 plus r right here. Okay, that was kind of bad. This is 1 plus r right here. Our decay factor is 1 minus r. Okay, and so everything else stays the same, initial amount and so forth. All right. So first of all, does this represent growth or decay? Well, it's going down from left to right, so of course this is decay, the decay graph. Okay, this is going up from left to right, so this one happens to be a growth graph, exponential growth. Okay. How about this? Is this growth or decay? And then identify the growth or decay factor, and what is the rate of growth or decay? So first of all, this is between 0 and 1, so it's going to be a decay. So it's going to be a decay factor is going to be 0.87. Okay. To find the rate, I'm going to take 1 minus r equals 0.87. Okay. So remember, that gives me my rate. So I'm going to subtract 1 from each side here. I get negative r equals, what is that? Negative 0.13, which means r equals 0.13. So that was my rate, which is 13%, right? So 13% decay rate. Now, some of you guys might be able to figure this out. Usually this number here and this number here adds up to 100. So whatever this is, you just subtract it from 100, and that will give you your rate, okay? So that's why you have, this basically represents 100, that 1 does. And so that's all you have to do with that one. This is a growth, right? This is a growth factor because it's bigger than 1. And so this is usually a little bit more straightforward. It's a growth factor of 1.25. Basically, since it's 1 plus, the growth factor is just the part that's bigger than 1, right? So it's 20.25 is my R. Okay? And so that's a little more straightforward than the decay. Okay, so here let's put it to use a little bit. Here we have an investment of $76,000 increases at a rate of, it's a rate of 12.5%. Find the value of investment after 30 years. So my final value, my Y, is going to equal my initial amount, which is going to be $76,000. Okay? Times, now this is an increase, so it's going to be a growth. So we're going 1 plus my interest rate. And so remember, we're going to move that decimal 2 to the left, so it's 0.125. So 0.125. Okay, so it's always in decimal form. And to the, and time is going to be 30 years. Okay, so there's my function right there. If I just simplify it, I go y equals 76,000, 1.125 to the 30th. And let's see what that is, how much investment we have here if we're going to be able to retire in time. So we have 76,000 times 1.125 to the 30th. That's pretty good, right? We got about $2.6 million. So we're going to say y is approximately equal to $2.6 million we're going to have after 30 years. That's fantastic. Okay. All right, our next one here is the value of a piece of equipment has a decay factor. So they actually give us the factor. That means we don't have to convert anything from percentages. Okay, so be careful with that. So notice it says decay factor. That's what we're going to plug in right there. We don't need to do 1 plus or anything. Okay, so we have our final amount. So after 5 years, the equipment is worth 98,000. So this is a little bit backwards. What was the original value? So my original value is actually, this is A. We want to know the original value. Okay. So my final amount is actually this guy right here, 98,304. They want to know what was the original value right here. What is A? We don't know that. Okay. And since we already have our decay factor, we're just going to put 0.80. And then our time is after 5 years. So this is pretty nice right here. I'm just going to go ahead and just divide by 0.80 to the 5th. Divide by 0.80. That was very good. To the 5th. And then we'll get our calculator up here and see how we do. Okay. So we have 98,304 divided by, we'll go 0.80 to the 5th. What was my parenthesis for the, oh, gracious. What happened there? Delete. Oh gosh. Okay. Here I'm just going to go 0.8 to the 5th. And then I'll take my 98,304 and divide it by my answer there. And get us about 290,844. So A is about 290,844 was my original value of that guy, which is crazy. And after 5 years, it depreciated to $98,000. Bummer. Okay. So car is purchased for $24,000. The function here can be used to model the car in thousands X years after it was purchased. Does the function represent exponential growth or decay? Well, it's 0.8, so it is decay, right? 0.8. Okay, depreciating by 20% a year. That's crazy. What's the decay rate for this function? So remember, you can just take 100% basically minus 80%, or 1 minus 0.8, and it's going to give us 20%. So just remember, you can take this 80% and take it away from 100%. That'll give you your rate. Okay. This says graph the function on a reasonable domain. What that basically means is if I plug in 0 here, take a table of values, I plug in 0, that's going to give me 24, right? That's my starting point. So if I come up here, we go 5, 10, 15, 20, 25, 30. This is going to be 24. That's going to be my y-intercept. Well, we're not going to go negative time, right? This represents time. So my domain here is going to be, my reasonable domain is going to be x is greater than or equal to 0. Okay. And so if I plug in 1, I'm going to get 0.8 times 24. So what is that? So yeah, 0.8 times 24 is 19.2. So this gives us 19.2. What if I plug in 5 years? What about 5 years? What happens? So that 0.8 times 24 to the 5th power. It gives me, whoa, what did I do there? Got 24 times 0.8. Oh my goodness. 24 times, getting late, you guys. 0.8 to the 5th power. There we go. That's 7, that makes more sense. 7.8. Okay, 7.8. Let's look at it after 10 years. Let's see what happens after 10 years. All right. So 24 times 8 to the 10th power. Let's see what happens. Oh, down at 2.6 now. Okay, so let's plot that. 1 is going to be up to 19 something. 2, 2, 3, 4, 5 is going to give us a 7.8 somewhere around there, and then 10 is going to be over here at 2.6. So you can kind of see it starts up here and it kind of starts to depreciate down here more and more. Okay. When will the value of the car be about 5,000? Well, we could plug this in here and go $5,000 equals 24 times 0.8 to the x power. We could do that, but then how do we solve for x? We're going to learn how to do that actually in a couple sections. Okay, but $5,000. Let's go up here to $5,000 and find out over here. It's about right here. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, about 5 years or so, right? Maybe between 5, maybe one more year, maybe 6. Probably I'm going to say 6 years, okay? Because we know 5 is 7.8, so I'm going to say it's probably about 6 years, okay? All right, so you have this is like a summary of everything with your difference between your decay factors and your rates. So make sure you understand the difference between those, the different equations, and then you guys have a worksheet in Google Classroom. And I will see you tomorrow. Take care. Bye bye.